So for example, you're a caveman, you're like, it's 5 o'clock, the sun is there. 5 o'clock, caveman. The saber-toothed tigers normally eat on this path, so I'm going to go on this path because I have a higher chance of dying over there. Now, did they actually use any of those words? No. Did they use those ideas? Yes. That's evolution, right? And let's not, please, your God, if you don't believe in evolution, maybe just leave. So don't bring that shit up. Flat Earth, no, stop. But other things about probability are not inherently understood by us. They're not hardwired in our brains because they didn't have to be to survive. But here's the problem I like to start with. We did the birthday problem, right? First day. I like to do that first day because that's when I have the most people in the classroom for various reasons. So here's the let's make a deal thing. At the end of the show, there would be 3 doors. Right? And behind one of them is the prize. It could be like a trip to Aruba or $50,000, whatever. And then behind the other 2 are goats. And let's assume that whoever's on the show is not there to win a goat. Right? They don't like, come on, goat. So here's door 1, door 2, door 3. I like it. So somebody pick one of those doors for me. 1, okay. All right, now stay with me. What's the chance? What's the probability that he won the prize?
33%.
Yeah, no, it's not right. It's 33.3333. So better would be how many out of what? 1 out of 3 chance. Why? Why? That's the most basic idea of probability. How do you do any probability? The number of things that match what you're looking for divided by how many things could happen. There's 1 door with a prize and 3 doors. So 1 out of 3 chance. Are you guys with me? So what's the probability the prize is not behind this door? 2 out of 3 chance, right? So right now I know the probability you win is 2 out of 3, and the probability you get a goat, probability you win is 1 out of 3, probably get a goat is 2 out of 3. Is that cool? We don't know anything, right? It could be anything. The host will now open one of the other 2 doors. So I'm going to open this door and show you there's a little spider goat. Spider goat, spider goat. Because that's, the extent of my... All right, we're going to leave it. That poor mutant joke alone. It's been through enough. Here's the question. Would it change the probability you win if you switch doors? If you change to the 3rd door? Would it change the probability that you win?
No, because it would put on.
Here's the funky answer. It definitely would. It would double the chances you win. Now go with me on this. Here we go. You ready? You already told me there's a 2/3 chance that one of the other doors has the prize, right? Why did I open this door? So I gotta open a door. If I open the door with the prize, show's over. You get your goat. Too damn bad for you. So I don't want that to happen. I want to increase the drama. So only 1 out of 3 times will you pick the prize, and then I can open either door. Does that make sense?
Yeah.
But 2 out of 3 times, you're going to pick a goat, and then the only door I'm going to open is the only door that has the other goat. So 2 out of 3 times, that door has the prize. And that is the door that I picked in my head to have the prize. Prize. Right? This has a little goat in it. Let me do this. You ready? Let's say I have this insane, huge studio where I have 100 frickin' doors. You with me? 100 doors. Somebody give me a number 1 to 100.
22.
22. So you picked the 22nd door. Right? Is that cool? What's the probability that she got the prize? 1 out of 100. What's the probability that the prize is somewhere else? 99 out of 100 chance the prize is somewhere else. What do I then do? I open every door except the second frickin' door. Why did I not open that second door? Almost for sure because it has the prize. Does that make more sense? If there's 100 doors, I open every other door except this one. I'm like, yeah, I only had a 1 out of 100 chance to get the prize. There's a much higher chance that this one has the prize then. Okay, maybe. Now, do you see how weird that is? Some of you guys are like, dude, I still don't understand what the hell you're talking about. Well, hopefully someone does. All because when I open a door, or I open 98 doors, I'm giving more information. That's why the probability isn't just 50%. There's a reason I didn't open that door 99 out of 100 times. There's a reason I didn't open this door 2 out of 3 times. Right? That's why it's better to switch. And Mythbusters did an entire thing. They built a whole set. They had people come in. They did an experiment and actually did this. And they did find out it was roughly twice the probability, twice the percentage of the people. If they switched, they won. Does that mean if you switch, you definitely will win? No. And that's where people start to lose faith in probabilities. It's like probabilities never try to claim that they can tell you exactly what to do. Right? Everybody's always trying to figure out how to get the lottery. Well, the number 14 hasn't come up in the last 6 months. So it's going to have to be... No, it isn't. Holy shit. It can be the same number twice in a row. You with me? No? I like it. If you played a lottery where you pick 4 numbers, would you use the numbers 1, 2, 3, 4? Would you?
I would. Why not?
Why not? Exactly. But I'm sure somebody's like, no, you want to pick random numbers, Jeff, because, but no, 1, 2, 3, 4 has just as much chance as 3, 5, 2, 6. Right? In fact, 7, 7, 7, 7 has just as much chance as anything else. Maybe? Maybe not. Okay. So part of why I want to do this is not, even if you don't quite get this idea yet, I'm hoping that some of you guys did. My whole intention with doing this is to show you that probability is not inherent in us. We don't have it hardwired. I don't do this to make you feel like, oh shit, I'm not going to get any of this. I do this so that you understand why we create equations for these, why we do have to consider what's going on, because it's not immediately hardwired in our brains. Okay, maybe. Okay. So let's do this. I kind of like to start off with the type of problem I love to give, and then we just analyze the shit out of it. Okay. So here's the kind of problem I like to give. I like to give what's called a contingency table problem. And I try to make these out of the answers you guys provided on the survey. So for example, let's say we have men and women, and then they answer a question, yes, no, not sure. Okay. Like, I don't know, do you agree with Trump's handling of Iran? Yes, no, not sure. If you don't know what's happening in Iran right now, let's pay attention. Holy shit. There's some big shit happening right now that you probably should be a little bit freaked out about.
Oh, God.
Let's forget about it for now. He just gave a statement this morning. I'm not sure what he said. Probably was almost coherent. I'm sorry, I can't even hide my feelings anymore. Thankfully, nobody with red hats here. All right. So let's say I ask people a question, and let's say 7 men say yes, 20 men say no, 3 say not sure, 27 women say yes, 5 men say no. I'm sorry, 5 women say no, and 2 women say not sure. Right? So I'm going to give you this. Now again, what's probability always related to? What's always on the bottom of a probability? The total number of chances, right? The total number of things that could happen. So if I picked one person out of this group, how many people could it be? Well, let's kind of piece this together. How many people said yes? 34 people said yes. You guys see that? This is the yes columns. How many total people said yes? 34. Is that cool? All right, how many people said no? That's crazy. How many said not sure? 5. How many men were there? 30. How many women were there? 34. Now, a special place in my heart for the poor person that puts 128 down there, you don't want to count everybody twice. How many people are there? 64. So what this better also have to be 64, right? So you gotta check yourself, but don't count everybody twice. Does that make sense? All right. So the basics of this table so far, nothing amazing, hopefully. Maybe. So if I pick one person at random from this group, what's the probability that they said yes? So this is how I represent the probability of an event. Yeah, well, careful. I like what you're thinking.
34 out of 64.
So if you think the answer is 1 out of 34, I didn't say, they did say yes, what's the probability it's Bob? Well, there's only one Bob out of 34 people say yes. I didn't tell you a shit about the person, right? I didn't tell you anything about the person, just what's probably they said yes. So how many people could it be? 64. Out of those 64, how many did what I'm looking for? 34. So it'd be 34. Match what I'm looking for out of 64 total things it could have been. We're going to learn several different formulas for probability, but they all have to adhere to this basic rule. A probability is the number that matches what I'm looking for divided by the total number that could have happened. Period. Maybe. Does this feel familiar to anybody? Have you guys this is basically finding percentages of a group, right? 34 out of 64 people, that's the percentage of the group, and that is the probability that you pick somebody then, right? How many people in here are left-handed out of curiosity? Anybody? I'm not left-handed, I'm just showing you, and I don't want you to raise your hand. Amy? You're representing all left-handed people. And let's say there's roughly 40 people. That's way less than normal. So normally it's like 10%, 11%, but for any group, it could be anything, right? So what's the probability if I pick somebody at random out of this group that I get somebody who's left-handed would be 1 out of 40 roughly, or whatever it is. Okay. So percentage very often is the same as probability if that percentage is like a relative, a relative frequency. Isn't this a relative frequency? What's the relative frequency of yes? Well, there are 34 yeses out of 64 total answers. I like it. What is this as a decimal? Take it out to 4 places. We're always going to take probabilities out to 4 places because I'm crazy. 0.5, 3, 1, so 3?
Yeah.
Okay. So you can also make this into, don't put approximately, there's approximately, and this is going to be 53.13%. Okay, how we doing? So for a probability question, this is the work. This is the way I want the answer, one of these 2 ways here. So if you don't show me the work and you get it wrong, I'm going to take off all the points because I have no idea what you did. Okay, lock it. So what about this? What's the probability that somebody wasn't sure? Yeah. That's really weird because I saw your mouth move and then I heard some dude talk and he had a really deep voice. 5 out of 64. What the hell is that? 8% almost. 0.078. 1. So 7.81% chance. Okay, how are we all doing? Is that so far so good? So I'd love to give you this kind of problem. This is just one kind of problem, but I almost always give this kind of problem. I give you the table, you figure out all the totals, because then you can answer any probability question I ask. So let's try one that's a little more interesting. So I'm going to change colors, watch out. What's the probability I pick a man or somebody who said no? Where are you getting 55 from?
35 and 30 and 25.
So now watch, this is beautiful. I love it, I love it, I love it. Whatever, Jeff. 30 men. If you add that to 25 no's, did you count anybody twice? Hell yeah. Can't do that shit. Right? No matter how much you want your vote to count 7 times over, hopefully it won't for anybody. We'll find out. All right. So I agree with you. 30 men. If I do plus 25 people who said no, I got to subtract off how much? Not 5. Because how many did I count twice? 20. Now what could you have done instead? Let me make sure you guys are all with me. So if I add these 30 to these 25, did I not count 20 people twice? So that's not fair. There aren't really that many people that do that. You could have done this. 30 men, how many said no that I haven't counted yet?
5.
Yeah, so it'd be 35 out of 64. And sure enough, what's 25 minus 20? Freaking 5. You guys see how all the math has to agree with itself? No? Okay, maybe. So what do we get there? We get 35 out of 64, which is, we do almost. So it'll be a little bit more than 53.
54.69%.
So 0.5.
5469.
69?
Yes.
Okay, you guys getting that? All right, so you guys do this one. What's the probability that I get somebody who's not sure or they're a woman? Excuse me. You can always just add the two together as long as you adjust it by getting rid of the people you counted twice. Right? Take them out, just get rid of them. So not sure, there's 5 not sures. There's 34 women. How many did I count twice? Yeah, these 2 I counted twice. So that'll be 37 out of 74, which is something.
0.5781.
Sounds right. 5781?
Mm-hmm.
All right. How are we doing so far? I mean, this, you really should be liking this. This is not anything too crazy. But look at what this means. Or will always make the answer bigger. So, for example, we're about to do an and problem. That's why I want to make a big distinction right now. Or includes more things to match. So if I said was probably, somebody said not sure, it was only 5 out of 64. I say not sure, or woman, now it's way the shit up at 37, because now I'm allowing for other things to match what I'm looking for. I'm looking for somebody's not sure or a woman. I'll take either one. So that increases the things that match what I'm looking for. So, or I call it the nice bouncer. You go to a bar, it's like, okay, to get in the bar, you got to dress nice. Ah, shit. You got to have a lot of money. No. Or you got to know Joe. I know Joe, and then I'm in. Yay, nice bouncer. And it's the mean bouncer. He says, I come up, he's like, all right, to get in the bar, you got to know Joe. I know Joe, and you got to be rich. I'm already out. And you got to dress nice. I was out already. Leave me alone. So, have you guys ever looked for scholarships, for example? Yes? Don't you like, nowadays there's sometimes you have an application to apply for all these different scholarships at once. It's crazy. Back in my day, right? Jeff's old. Go to the financial aid office. There's a book about this big that they'd update every month or something insane, so a lot of trees were just dying back in the day, kids. You go in there, you open this thing, and you start reading, okay, to get this scholarship, you must be a math major. Check. You must have a GPA greater than this. Barely. Check. You must do this, you must do this, you must do check. You must be a woman. Why don't, this is a real story, by the way, guys. I went through all this shit. Some of them were kind of freaky, and then I'm like, why not put that at the beginning? Turn the page. Shit, next one. Right, so and will always make the probability smaller because to get in, you have to do both things. Or in that case, the whole list of things. How we doing? I like it. Anybody going for the nursing program? Isn't there a list of things you have to do to get into it? This and this and this and this and this. And if you only have one of them you don't do, you can't get into that. Sorry. And even then, you got to get on the waiting list. All right. So let's do an and problem. Let me see. Where can I put this business? Too far away from everybody. 5. What's probably I get somebody, a woman, and they said no. Yes. Because how many people do both? You have to be a woman, and you must say no. So look at this cool thing. What an and is also called an intersection. That makes total sense. It's the intersection of those two things. 5 out of what? Every single one of these has been out of 64 because it could have been any of the 64 people. 11. And 5 out of 64, we already know. All right, let me stop there for a second. And should always make the answer smaller because there's more things to match. Or makes the answer bigger because they're including everybody in all those different categories. Okay, maybe. All right, here comes the freakiest one. Let me see, I'm going to take these basic ones away because these are oldies, these are easy. Yeah. What if I said this? What's the probability I get somebody who said yes, given that they are a man? So do I know something about the person now? And let me be careful when we say that. Let me say this again. It's the probability that they said yes, given that they're a man. So what do we know about the person? They're a dude. So how many people am I talking about now? 30 people. So what goes on the bottom? 30. Yeah. So whatever's given, that's what it's going to be out of. Because now I know I can throw out all the women. Sounded terrible, but you get them out of here. You guys with me? I think somebody only heard that last thing I said and they looked mad at me. I'm sorry. We can discount all the women because I know it's a dude. Out of 30 dudes, how many did what I'm looking for? 7. Bam. 7 out of 30. What is that going to be like? 0.22? What is it? 0.23. 0.23?
Yeah.
So either way of that, I like it. So that's the work. And this is how you can give me your answer. I like it. So let me do one more thing and then we'll take a break. We've got, actually let's do one more given problem and then we'll construct these equations and then we'll take a break. Well, let me see, I was trying to number these. This is a 6th example. 7th example, what's the probability that I get a woman given that they're not sure? And the mistake people make is they put the wrong number on the bottom. What do we know about the person yet? It should be out of 5. Because I know, given they're not sure. So out of 5 people, how many match what I'm looking for? 2 are women out of 5 that said not sure. And that was nice. That was good. good old 40%.
40%.
Maybe. Maybe.
I have a question.
Yes.
Why wouldn't it be, why wouldn't it be 34? Like, why is it 5?
What is it that I know about the person? What did I give you? So again, read this. The probability that they're a woman. So I don't know if they're a woman. Given that they're not sure. So what do I know about them? They're not sure. I don't know if they're a woman or not. I don't. What's the probability that they're a woman given that they're not sure? So how many people am I talking about? 5. Because what do I know about the person? That they said they were not sure. So who can I throw out? All these people. So how many people am I talking about now? 5. Out of those 5, how many are, where am I at? Are women? 2 out of 5. So you can actually do that. On the given, it's called a conditional probability, which kind of makes sense. On the condition that this is true, what is this probability? That's where that word comes from. But anytime I give you a given probability, with a table, kicks ass, because you just cover all the other shit up. So on the one that said given a man, I would just cover this up. There's my whole world, right? My whole world's men. All right, you guys with me? Yeah, I like it. I just want to say that because it sounded very creepy. Okay, maybe. So, last thing here before the break. I want to develop. Now, one thing I want to point out. Have we used any real formulas up here? We've just used an idea, right, to construct the probability. We haven't done anything about formulas yet. Stay with me. This is something I'm not used to math people saying. The formulas get in the way if I give you everything to count. Probabilities are really simple. They're all about counting. If I don't give you anything to count, then you have to use formulas. So we're actually going to develop the formulas based on what we did just because it made sense according to the idea. We're going to create the formula now based on what the hell we did. So let's look at OR, for example. Everybody with me? You guys all right? I'm always curious what notes look like for me, but let me take this one. Let's just focus on this one up here. Help me out. So this is the probability. Let me make this, let me just do this and I'll make it more general. So just to put this in symbols, what is this? Where'd that come from? What was that? Probability of a man, right? Plus, what's this? Probability that they said no. And then what's this?
Subtracting the men back up.
What exactly was the 20?
The men who said no.
Repeat it.
So be very specific that they are a man and they said no. Right? Did we need that formula to do it? No, because we did what the idea makes sense. But now I can develop a formula that will help me on problems where I don't have all these numbers to count. That's beautiful, and that's the thing that you guys don't get to see very often is how equations come from ideas. Standard deviation, we started with the idea, we made an equation that went with that idea. That's beautiful. You guys are so used to just, there's an equation, kids, plug shit in there, and pray. Right? So, I love this because you get to see more of this stuff. Let's look at given next. This is going to be a little bit freaky. Oh, let me make this more general. So here's what's going to be on our formula sheet because I'm not going to give you a situation with men and no's necessarily. So the probability of event A or event B. They ask you for the probability of this or that. And you have to use a formula. It would be the probability of the first dude plus the probability of the second dude minus the probability that I got something that's both. I got to subtract those off because I don't want to count them twice. That is the official OR formula. I like it. We saw what we did, and we made a formula that captures what we did. Let's look up here at the given. Yes?
Is that an and or an or on the bottom?
Here?
Yeah,
Let's try to be an and.
okay.
Sorry. I like it. So let's analyze this given dude. So let me see if I can, yeah, yes. And let me go ahead and give you the symbol for given. There's a symbol for given that I'm just going to start to do if I'm not careful. Given. Straight up and down line means given. Probably said yes, given they're a dude. What was this number related to? Men. Let me see if you guys. So on the bottom goes the probability of the given piece. What was this? 7.
They say yes.
More specifically, why just 7?
A man that said yes.
Yes. So this and this. So on the top goes that and that. Because if I know men happened, that's a really weird phrase. But if I know that I got a dude, what's the only way they could have also said yes is if they're a dude that said yes. If they're a woman that said yes, they're not going to get included. That's why it makes sense that top is an and. The only people who said yes that I'm going to include in this problem is if they're yes and they're a dude. Because they know it's a dude. Okay, maybe. Even if you don't understand what I just said, that's the formula. So in general, the probability of event A given event B is the probability of A and B divided by the probability of B. Now, I probably, if I haven't already lost you, I'm going to go one step further because I know somebody out there is thinking to themselves, that ain't no probabilities up there, Jeff. What is the probability of yes and man?
7.
7 out of what? No. Probability of yes and man. 7 out of 64. What's the so? Do you see what I'm doing? I'm going to do the formula. Do you see how already it looks not right? All right. What's probably it's the dude? 30 out of 64. What happens to the over 64s? They 7 out of 30. Sweet. Okay, just in case somebody was like, those aren't probabilities, Jeff. Those are numbers of people. And I know somebody out there maybe was thinking that. But the bottoms will always cancel. That's why it matches up. Okay, maybe that's enough for right now. Let's take a break. Come back 10:35. If anybody didn't get their test back, come up here.